So here we are in the next section of Chapter 9 on circles, Chapter 9.5 or Section 9.5 on tangents. So this word tangent has been used a few times throughout the year in a couple different contexts. We've used it in the context of circles, which we are in this unit, and we used it in the context of trigonometry when we were looking at the ratio between the opposite and adjacent sides of right triangles. But back to our work with circles here. A tangent is a line. It's a line in the same plane as the circle that intersects the circle at exactly one point. Okay, so it's a line, not a segment, and it crosses the circle exactly once. That point at which it crosses the circle is called a point of tangency. Okay, so over in the diagram here, you can see here is our tangent line. Notice it crosses the circle exactly one time, circle C, and that point at which it crosses right there is our point of tangency. Okay, so it's described right here. So AB is tangent to circle C at point A. But you could also have a segment AB, so if you forget about the line, and a ray that could also be tangent to the circle, but generally we're talking about a line. A couple other terms here. So a common tangent is a line, ray, or segment that is tangent to two circles. So notice that this tangent line crosses this circle once and it crosses circle F once. So it is, they have a common tangent because it's tangent to two circles. And this one, where it kind of goes right down just at that one point where those two circles meet, that would also be a common tangent to those two circles. All right, so some theorems related to tangent. What is true about how these tangents intersect, so to speak, with circles? So in a plane, a line is tangent to a circle if and only if it is perpendicular to a radius drawn to the point of tangency. All right, so here's one of those biconditional statements. So a line is tangent is always going to be perpendicular to a radius that goes out to that point of tangency. So if we have the line and its tangent, it's perpendicular to the radius. Conversely, the radius is always perpendicular to the tangent line at that endpoint, at that point of tangency right there. So that will always be a relationship. So let's apply that theorem here. So we see this radius here of 8, and we see a tangent here, KL. So it says JL is a radius of circle J. Determine whether KL is tangent to J. Justify your answer. Okay, so we're actually determining whether this is going to be a tangent segment or not. Okay, so given this, and 9 right here is the length of just this piece right here, actually, because we know that the radius right here is going to be 8. So let's just be careful with that right there. And that's a little unclear, but yeah, so this then would be 8 because that's a radius. This is 9, so that whole thing would be 17. And so if this is a tangent segment, remember it has to be perpendicular to the radius. So this has to be a right angle, and therefore this would have to be a right triangle. So let's use the converse of the Pythagorean theorem. Let's ask ourselves, is 8 squared plus 15 squared equal to 17 squared? If it is, then this is a right triangle, and that would be a right angle, and therefore this would be a tangent. All right, so we got 64 plus 225. Is that equal to 289? And I'm thinking it is, right? 64 plus 225 is equal to 289. So, yes, this is a right triangle. Angle JLK is a right angle. So KL is a tangent based on our theorem from above here. Okay? All right, let's do a little bit of work on example 3. So let's take a look at what we got, kind of similar to the last one right here. It is saying that JH is tangent to circle G at point J, point of tangency J. Find the value of X. So we do know that this is a tangent, and therefore this is a right angle, and therefore this is a right triangle. And so now let's go ahead and determine the value of X. Okay, this one is going to bring out some algebra that we haven't worked with much lately. That's kind of exciting for me though. So this hypotenuse right here is going to be X plus 8. So doing the Pythagorean theorem here, we have a squared plus b squared, so x squared plus 12 squared is going to be equal to x plus 8 squared. A squared plus b squared equals c squared. All right, let's recall some of our algebra here. So let's see, x squared plus 144. Now, remember, this means x plus 8 times itself, x plus 8, which is not the same thing as x squared plus 64. Remember, if you FOIL this or use a rectangle diagram, and in our algebra classes these days, oftentimes we like to use the rectangle diagram. So x plus 8 times x plus 8 really means that you're multiplying two sides of a rectangle, which can be divided into 4 little parts here. So x times x is x squared, x times 8 is 8x, x times 8 is 8x, 8 times 8 is 64. And then we add up each one of these individual areas to get x squared plus 8x, which is total of 16x, plus 64. You could FOIL that too. So if you learned that last year, first times first would be x squared. Outside ones would be 8x. Inside would be 8x. And last times last would be 64 as well. So you get those same 4 pieces, just a different method. Okay, so when we do our algebra here, we get x squared plus 144 is equal to x squared plus 16x plus 64. We multiply that out. All right, so now let's see what happens here. If we start solving for x, notice we undo the x squared from one side, they actually cancel out from both sides. So that leaves us with 144 is equal to 16x plus 64. Okay, now it's looking a little bit better, isn't it? Subtract 64 from both sides. And then that gives us, what, 80 is equal to 16x. And then dividing both sides by 16, we get x is equal to 5. And that is our solution here. I guess that's all it asked us to find. So the radius, therefore, is 5.